So one of the most important reasons why I'm interested in spending so much time discussing Euclidean geometry instead of Minkowski geometry is that I want you to be comfortable in using tensor notations. That is basically the notation using the indices. And this is very important for us because this will allow us to understand the importance and the role of metric tensor, especially the role of metric tensor in geometry. So before getting there, I'd rather start by reviewing what we have derived in the last lecture, that if we do not consider stretching or inversion for that matter, nevertheless I'll consider inversion first in general, but mostly we're interested in rotation. But let's just include all the coordinate transformation that does not involve stretching. So in that spirit, in the last lecture we wrote that a vector transforms under the rotation like this. There is a rotation matrix or an operator we can presume that acts on the initial vector, or more or less the coordinate system, and rotate in such a way so that we get another vector in the rotated coordinate system. In this case, I must distinguish between the active rotation and passive rotation. So by active rotation, I mean the vector itself rotates, and by passive rotation, I mean a rotation where the vector stays the same, but only the coordinate rotates. And when we are talking about rotation in this manner, we're talking about passive rotation, not active rotation. So that's a little bit of trivia we must think of before we go on. And we also had a case where there is a similar sort of relationship acting on the position vector. Now, the way we distinguish between these two cases is by taking the determinant. So determinant of L rotation will be 1, and the determinant of L inversion will be -1. In some cases, it's +1, as I have explained earlier. For example, if we invert the coordinate system with respect to 2 axes, then it becomes equivalent to a rotation. But for example, if we just invert 1 axis, it's a discrete transformation. If we invert 3 axes, it's a discrete transformation, and so on. And this transformation rule is essentially the cornerstone of understanding vector. If I ask you what is a vector is basically a geometric object that has a certain transformation rule. So we can take any vector, for example, x or y or a, any vector, and under coordinate transformation we'll have an operator and we'll have the previous vector. I should pose a prime here, and this can be any vector, to be honest, and that vector must fulfill a certain transformation property. Now, as we explained earlier, that if we represent the vector as a column matrix, for example, some a x, a y, a z, then these are, in this case, 3x3 matrices, and if this is an n-dimensional vector, then these are n×n matrices. Now, as we know from elementary vector analysis, if we're given a vector, we can find out its norm or magnitude, and the way we can do that, for example, in Euclidean geometry, is simply we write 2 bars in both of its sides, and we write ax squared plus ay squared plus az squared whole to the power half, or basically it's the square root. And we can actually write the square of the norm by writing it as a squared, which basically means that the dot product of A with itself, and that is a x squared plus a y squared plus a z squared. Now, if A was an n-dimensional vector, we write its norm squared as a dot A, which is a1 squared plus a2 squared, so on up to a n squared. However, here is the leap we take forward. Whenever we write vector components like these, we'll start writing them as a I. So instead of the subscript, we write in the superscript. So this is not power, but it's simply an index, right? I can be 1, then it could denote the first component, and I equal to 2 will denote the second component, and so on. And so if we have a vector A, and if we write it as the column matrix, then we write as a1 up to a n. But now one of its components will be denoted by writing a I in the superscript. So I can be 1 up to n. Now, if we write a vector of any dimension, let's just say n dimension, if we write a vector in such a representation, which is a column matrix representation, then I can find out the norm of this vector by writing A transpose A, and this will basically give me a1 an times a1 an, and according to the rules of matrix multiplication, this is simply a1 squared plus a2 squared plus up to an squared. So this is precisely what we understand by the square of the norm, which we write as a squared or a dot a or a magnitude squared. So this thing here and this thing here, we call this operation transposition, but this is an integral part of defining the dot product of a vector, this operation, which is the transposition. But we mentioned that this column vector, this column matrix, is simply a representation of the vector. We have seen that we can represent a vector in many ways, in many notations, and this is one of the ways. So this transposed row matrix must be the representation of some sort of vector. And this one, we call it a representation of a dual vector. So definitely we'll need notation to distinguish between a vector and its dual vector. Now, there are lots and lots of geometric discussions, books, which discuss this problem from various angles, from other elegant formulations, but we don't have to go in those directions. What is important for us is the concept of a vector and the dual vector that we need in order to find out what is the norm of a vector, the norm square of a vector, or more generally, the dot product of two vectors. Those two vectors can be the same vector or different vectors. So let's find it out. So if we are given a vector, then there is a column vector representation, a1 up to an, and we write a component of this vector as a I. Now, this index, this superscript, we call it a contravariant index. If we take a dual vector, so in order to represent this dual notation, we write a bar not above but beneath this symbol. So there is a one-to-one correspondence, and this dual vector in this representation is written as a row vector. And we denote a component of this dual vector as I as a subscript, and this subscript I is called a covariant index. So whenever a contraction or a summation takes place, for example, A dot A is basically the summation of A1 into A1 plus A2 into A2, and so on, plus AN, then we're simply writing it as AI. So from now on, whenever we will create a contraction of indices, it will always take place between a covariant index and a contravariant index. So this is a contravariant index, this is a covariant index. By the way, I've written it wrong. This will be actually contravariant. I apologize for that mistake. So in this period, we also write our vectors A as AI, EI hat. And as before, the contraction is taking place between a contravariant index and a covariant index. Now, this is the place where we can define usefully the concept of what we call the metric tensor. It's a tensor we write by the notation G mu nu, but in this case, instead of mu nu, we will write I j. As you can see, there are two indices. That means it's a second-rank tensor. Either one or both of these indices can be contracted with any contravariant indices. So how do we define metric tensor? This is, of course, written in the component form. If we write this in the abstract notation, we write this as only G, possibly with a bar beneath it. And we think of it as a machine that takes two vectors, let's say A and B. And it will have a couple of properties. One of the properties that it will have is that GAB is equal to GBA. That means it is symmetric in both of its arguments. And this is what we define to be A dot B. I'll speak more of it in the next video.